In this chapter, the generation of an accurate three-dimensional geometry of an aircraft propeller is performed. The three-dimensional propeller geometry is defined, specified, and created using several different parameters. Note that the definitions described here are identical for both aircraft propellers and marine propellers. The first parameter is the diameter. The diameter of the propeller is the largest circle described by the rotation of the propeller. The next parameter is the pitch. The pitch of the propeller is the geometric forward advance of the propeller for one complete revolution. This value is typically constant for all blade sections of the propeller. The pitch value is commonly reported at the 75/100ths or 3/4 radius position. The propeller pitch is dependent on the blade angle. The blade section angle is measured relative to the propeller disc. The next parameter is skew. Skew refers to the backward or forward displacement of the propeller blade sections in the direction of the pitch. From a front view, skew appears as a curvature of the blade. The next parameter is rake. Rake refers to the inclination of the blade sections in the direction of the propeller axis. From a side view, rake appears as a tilt or lean of the blade. Propeller blade sections are typically based on airfoils. Airfoil shapes are defined using several parameters. The most important parameters are chord, thickness, and camber. With few exceptions, the blades of a propeller are identical and repeated. Therefore, it is sufficient to create only a single blade geometry and then generate the full propeller geometry by repeating and rotating the blade around the propeller rotation axis. There are many stages in the engineering of aircraft propellers and turbomachinery blades that can be performed using STAR-CCM+. Examples include design, analysis, optimization, reverse engineering, and troubleshooting. A wide range of engineering disciplines may also be involved, such as aerodynamics, heat transfer, structural analysis, combustion, corrosion, erosion, fluid structure interaction, and others. Every simulation begins with geometry. The turbomachinery blade is one of the most critical components of the system. Therefore, throughout the various engineering stages, and for any of the topics mentioned above, having complete control over the blade geometry is extremely important. Blade geometry can be created using different methods and various software packages. The objective of this chapter is to generate a complete propeller blade geometry directly within STAR-CCM+. There are several important reasons for doing this. First, it eliminates the need to use additional software. Second, it improves the efficiency of the simulation file and allows design updates to be performed much faster, more easily, and more accurately. Third, it provides the foundation for creating a parametric propeller geometry so that in a separate tutorial, we can develop a fully parametric geometry generation process. Fourth, while creating the geometry, some of the fundamental concepts of propeller and turbomachinery blade design will be explained. This will help establish the necessary familiarity and background for the topics covered in later chapters. The method presented in this tutorial is a fundamental and classical approach. Therefore, similar procedures can also be applied in other CAD software packages. The propeller selected for this tutorial is a NASA 3-blade Supersonic propeller. The experimental tests of this propeller were conducted in a wind tunnel. The propeller geometry, test conditions, and experimental results are reported in NACA Report 1375. This report has been downloaded from the NASA website. This propeller is of the variable pitch type. The tests were performed at different pitch angle and for various upstream Mach numbers. The highest Mach number of the flow is 96/100ths. It should be noted that in general, propeller propulsion systems are typically used in subsonic speed regimes. However, this propeller was designed for a wide range of Mach numbers greater than 0.6 and less than 1 in order to demonstrate the efficiency and performance of the propeller within this operating range. There are two main reasons for selecting this propeller. The first reason is the availability of sufficient and relatively complete geometric data. The second reason is the availability of enough information to simulate this propeller under different operating conditions. The simulation of this propeller will be covered in another chapter.